Okay, good afternoon and welcome. So my name's Asad Samdani. I'm one of the Oracle Solutions Architects at Dell Technologies. I have a couple of very esteemed colleagues, Taisha Dorashina and Caillou, on the call with myself, and one name that's not on there that I shouldn't forget is Bart Serps. Unfortunately, I forgot to put his name on, so my bad. Apologies for that, Bart. I'll leave it to Taisha and Kai to introduce themselves in due course. But this session is about the use of Intel Optane persistent memory with Oracle. Ty, if you just wouldn't mind moving on to the next slide, I'll just go through the agenda for this session. Taya? Taya, I'm not sure if you can hear me, but could you just move on to the agenda slide?
So internet connection is not good.
Okay. I think she's just coming back in now.
Lovely. I've just double checked and she has got the power to share her screen now as well.
Okay. Thank you, Taya. Apologies for that. Taya's going to start off by doing an introduction to PMem, what it is, how it's used, how it can be implemented in Dell servers, and then she'll look at how to use PMem in database in memory option with Oracle, and some guidelines around designing systems with persistent memory to use Oracle databases, and some test cases that Dell has gone through and documented in the last year or so. And then she'll hand over to Kai, who'll talk about using PMem in app direct mode, which is the second mode of operation for Intel Optane PMem. And that's again with Oracle databases. So Oracle have recently announced support for certain mode or app direct mode with Oracle databases. So he's going to go into that. And then at the end of that, we'll open it up for questions and an open discussion. So what I'll do is I'll hand over to Taya now. Taya, if you want to continue with the introduction to PMem, and over to you.
Thank you, Asad. Hello, everyone. My name is Taisha, and I am Oracle Solution Architect in Dell team. Previously, I was working for 3 years in Oracle as data analytics and the BI specialist. So the topic of data management and in memory systems, it's somehow close to my heart. So what is we're going to have a quick refresh. What is a PMem? Even having in mind that most of you most probably heard about it, just to be on the same page. So PMem is one of the worst technologies which were designed specifically as an answer to the challenge of growing data and the growing price of managing of the data. First, PMem is a byte-addressable memory device, which is resides on the between DRAM and the normal storage media. In terms of speed, it's still 10 times faster than SSDs and 10 times less than DRAM. And it's the technology which becoming more and more important, having in mind that DRAM is one of the most expensive components of the systems. So in other words, PMem is able to deliver the bigger volumes of memory, but for lower price, and the trade-off is partially speed. The modern third generation of Intel CPUs nowadays have 4 memory controllers each with 2 channels, and in total it gives us 16 slots for memory. And that in other words, it says that their configuration, which we able to have with PMem and the DRAM in total, having in mind that the largest DRAM capacity nowadays it's 128 per piece, and for persistent memory it's 512 megabytes. So on the slide there is an example of the real life server which you can buy from stock with configuration of DRAM and PMem 1 to 4, and it able to leverage 8 terabytes of memory in memory mode for your application and for Oracle data. And another 2 terabytes of DRAM capacity will be dedicated to cache. So the persistent memory have 2 main modes. It's a memory mode and up direct mode, as I already mentioned. And the difference is how, in this case, is a PMem treated by applications. In memory mode, application should not be changed, and the PMem will be visible from OS level and from application level like normal memory, and nothing have to be changed. For example, as we're going to talk about Oracle in memory option, so you can use this capacity for in memory or for SGA, whatever. And the same with other applications, they just will be able to see the higher capacity of memory. And controversial with persistent memory in up direct mode. Applications have to be aware about PMem, and there is a special DAX file system which has to be supported by OS. And in this case, application able to manage whatever it wants to put data in memory, which is faster, or in persistent memory, which is slower but still faster than normal SSD or HDD. So, and in terms of Oracle, it brings us several use cases. So the first part, persistent memory in memory mode, I will cover, and the persistent memory in up direct mode will be covered by Kai. And in persistent memory mode, as I said already, PMem will be recognized as a normal memory. So that means we can resize SGA, or we can resize SGA in memory capacity, or use it for OS purposes as well. So it's supported for all database versions, regardless what version of database, Oracle database you're running right now, you can use it. And just a small technical detail, the recommended capacity between DRAM and PMem, it's 124 to 116. And the PMem with up direct mode, it's something new which came with our latest Oracle database updates. So in Oracle 9C update 12, it's possible to store database files on PMem using Oracle memory speed file system, and then latest release of Oracle database 21C, one of the latest, it's possible to store the database files with support from OS. So let's switch to Oracle database in memory with PMem memory mode. So there is a white paper which were published by Dell Technologies a couple of years ago. And my goal is to provide you highlights on things which we find in this during this study, and then I encourage you to take a look on the white paper and dig on the details and make your tests after the presentation. The quick refresh, what is Oracle in-memory option? Oracle in-memory option, it is option which allows to run OTP and OLAP workloads on the same system. That means that our data resides normally on storage in the relational data. However, thanks to the in-memory option, it's also stored in columnar format in memory. And the columnar format, of course, it's first of all, it's famous for optimizing analytics and for better compression. And there are two things which are really helped in terms of database. First, it's a vector processing feature. That means that the in-memory option, CPU able to perform matrix operations within one cycle. Practically, that means that if you have this SQL statement with where clause, that statement can be proceeded in one CPU cycle. That means that our analytical operations become much quicker. And the second thing which helping to host two type of workloads on the one system, it's a replacement for analytical indexes. So that means that if you don't have in-memory option, you have to create a certain amount of analytical indexes to make your BI or other analytical queries processing system faster. And with a mix of OTP workload, that indexes have to be all updated with every transaction, and it creates a lot of delays for OTP, and everything becomes slower. And with in-memory options, you don't need those analytical indexes because information already in memory and columnar format, and it's sufficient, as already discussed. And so you simply can drop them, and that will release CPU power, and that will release OTP workload from unnecessary work and updates. And coming to compression, there are five levels of compression available in memory option. And Oracle, according to Oracle technical documentation, the compression level achievable, it's from 2x to 20x, depending on the data you have and the data types you have. So we will see later what level of compression we achieved during our tests. And coming to the description of the test environment. We did two series of tests with different level of compression. So let's first take a look what level of compression we achieved. On the drawing, you can see the required memory size in gigabytes for different compression levels with different sizes of data sets. And in our case, with highest level of compression, which is capacity height, we achieved compression of 3x. So that's pretty much good. Just to avoid questions during the presentation, how was done their memory sizing? The idea was to have enough in-memory space for placing in memory the data set which have the highest level of compression, and to balance the rest of memory between other components. At least one test was done with that logic, and other tests was done in a logic to have enough of SJ and PJ's place for as it could be, as we could imagine for normal database. and to allocate the rest memory for in-memory purposes. And there in test results, we will see how does it fit. So as I said, we did 2 series of tests, one with 1 terabyte schema, another with 3 terabyte schema. And there was 2 servers in both cases. And first server was DRAM only, and with 1 terabyte, it was 768 gigabyte DRAM. And the second was a mix of PMem and DRAM. So PMem was leveraging 1.5 terabytes capacity, and the DRAM was using as a cache with 768 gigabytes capacity. And for test sets, the numbers on the slide, so everything is doubled. And the data set is 3 terabytes. So let's take a look on test results, and then we will go to findings. So the results for 1 terabyte schema. In both scenarios, we run 22 sequential queries of 22 sets, and their workload was OLAP, and the tool which we were using was Hammer database tool. And what is important to mention here, that this capacity high, as I said, we don't have a data spill on disk, and with another level of compression, which is query low, we have a data spill on disk. We will have these marks on all graphs, and the drawings show us the query set execution time, which were normalized to values to capacity high for DRAM only. So taking the results of DRAM only capacity high test by 100, everything is scaled relatively to the test. So that means that the difference between capacity high test 1 and query low test 2 is almost 6 times, and we'll discuss the results later. And the same presentation for 3 terabyte test. We did series of 3 tests, capacity high, capacity low, and query high. And with DRAM only configurations, in 2 tests, we had their data spill on disk. And for PMem, there is no spills. Their query set was, the test itself was the same. And there again, the difference was just between their levels of compression. So let's take a look on the key observations. So the first question, so what is faster, DRAM or PMem? So the simple answer, of course, DRAM is faster, unless we have a small schema. So in our observations, we found that with small schema, which was 1 terabyte, DRAM only environment was significantly faster. So it's more than 30%. And just to be sure, we checked in AWR reports that in both cases, all data was populated in memory. Their PGA in memory sort was 100%, and their IOPS to disk was close to 0, so it was within 1%. So, and the conclusion from that observation that processing in such small schemas is primarily driven by main memory media speed. So if you're running really small data set, it could make sense to have just DRAM only configuration. However, if it's growing, So in our test, it was a 3 terabyte schema. And if we take a look on the same results, so with the same level of compression, we will not find the significant difference. It's nearly the same. And the root cause for that regardless of difference in the PGA size, which were 9 times. So the PGA size for DRAM only configuration was 100 gigabytes, and for PMem configuration was 900 gigabytes. In both cases, in memory sort was not able to complete fully in memory, and we had some IOs to disk dump area, which were within 15% for both cases, and that creates significant latency, and that eliminates the difference in memory media speed. So for higher data sets, it's possible to use PMem without any loss of speed or affecting the latencies. And another question which we want to ask, what is better, to have space-saving compression, which allow us to bring more data in memory, or query optimized. And here, the situation is nearly the same. It depends. It depends on their data set size. So in 1 terabyte environment, we found that the difference between processing time between capacity high and query low was not very big. So it's nearly the same. However, with 3 terabytes schema, we found that the decompression affects the results significantly. About 20% of query processing time can be saved in that scenario, and the root cause for that behavior is that in the case of capacity high, almost all data have to be decompressed, which were shown in AWR reports, and the conclusion definitely that if you have a choice between DRAM and higher capacity, high capacity, high compression, and lower compression, but PMem probably is PMem is better option, and I will show next results. So what is the next observation? It's exactly about the point that what you would prefer, DRAM but with higher capacity, or PMem, which is slower, as we know, but query optimized. And the results from our study shown that in case of larger data sets, it's more beneficial to have less compressed data, as I already said, because of saving the CPU cycles on decompression the large data set. And something very obvious, but why don't you talk about it? What if your data doesn't fit in memory? So we have a data spills, and there are, in both cases, whatever it's 3 terabytes or 1 terabyte, we will see that it's a significant negative impact on query performance, and it's definitely not the option you want to choose. So, summarizing my part before handing it to Kai, there are two main observations about using PMem and in-memory option. First, PMem will allow you to have a more memory size that can help you to avoid data spill on disk. And the second benefit from that you will have you can bring less compressed data to in memory, and both will positively affect their query execution time. So here is once again the link to white paper, and I encourage you to read it in more details and to make your own test. If you have any questions at this point, you can put it in the chat or open your mic and ask them. So, Kai, the stage is yours.
Thank you, Ty.
Thank you. So, so I can start sharing the slide, or
yeah, go for it.
okay. Thank you, Tanya, for sharing the persistent memory for in-memory database. So now let's explore the second mode for using persistent memory. Now, let's see how we can leverage the app-addressable for Oracle database. Just a little bit introducing for myself. So I'm actually working for Dell EMC Database Solution Engineering Lab here in Austin, Texas. So it's great to meet UK OEG colleagues. In last, I guess the last few years, I actually came to UK OEG and also the Scotland UK OEG conference. So it's great to meet the colleague again. And I've been working on Oracle database for almost 30 years, starting as a DBA, working in Dell and other database engineering team for 10 years. Then before I moved to the Dell Database Solution Engineering team, which aim to provide the best practice and performance study for the customer who run Oracle database in Dell or EMC infrastructure. So let's, Tony actually gave a quick introduction about the two configuration mode for persistent memory. And one is a memory mode, the second is the app-direct mode. And as Tony presented, the memory mode really, the great benefit of memory mode is actually provided the much bigger memory footprint that you actually can cache the entire database. So to the memory, to the system memory, which in this case is based on the persistent memory, because persistent memory has larger capacity and also relatively less costly than the DRAM. So the best use case is for in-memory database, because normally the in-memory database tend to use for OLAP application. In this case, most OLAP databases are much bigger, and that normally cannot fit into a DRAM. So obviously the PMem memory mode is a great candidate for that. You already saw that the performance-wise, the OLAP, the persistent memory mode actually provided, almost similar to the same speed, same performance as a DRAM, but you actually by using PMem, you actually have much bigger capacity to actually cache the entire database. So, but this also only help solve half of the story. Another half of the story is in a lot of database, such as OLTP database or mixed workload database, you have a very, very high I/O latency, which your in-memory mode cannot solve, because even you cache database, you still have a write, which in some heavy write database, such as OLTP database, it is a write, such as the redo log write actually block all database performance. That's why we actually need to think on another solution, that how we actually can speed up the storage, make the I/O much faster. Because in-memory memory mode is try to avoid I/O, but for read, but ultimately you still have to deal with the write I/O. So the app direct mode aim to solve this problem by allow database or other application to store the data in the persistent memory. Why we can do that? Because when persistent memory configured as app direct mode, it is non-volatile, which means when you shut down the system, when you have power down, your data still stay in the persistent memory, not like a memory mode, because your data in memory mode is not volatile. It's volatile, so you lose data when you shut down when you have power off. So that's why app direct mode, you have to configure persistent memory in app direct mode in order to have persistent data, and this basically will improve all the workload and all type of database. But this is an ideal goal, but it's not as easy as we just said. So reason for that is we have to take a look at PMem's the characteristic of PMem. PMem, when you configure as persistent mode, app direct mode, they are different from regular SSD or hard disk. One difference is they are block-addressable media, which means you actually read the data by byte, not by block. So in database, Oracle database, you configure as AK block. If you configure OS block, is like normally 512K. So, but PMem itself is read by byte. That actually could potentially create a problem, which we're going to discuss shortly. Second thing is the PMem app direct mode is configured as direct access, so which means that you actually can store the data. You can your CPU can directly read the data from the storage without going to the DRAM. So that is actually a great benefit. So you basically can bypass the I/O from storage to DRAM. So that is a benefit. But in order to achieve that benefit, your application has to be able to handle that, has to be aware, DEX aware. And normally, normal application without change, they don't provide such capability. So one is two categories. One is block-addressable, that could potentially create a problem. Second is how you actually can achieve the DEX mode and the benefit of the DEX mode. So let's take a look at specifically why we need that for Oracle database. Just repeat what I just mentioned. In a lot of OLTP database, we actually, if you look at the AWS report, especially for those high workload application database, you will see a huge I/O weight. In this case, I just show example. This is almost 5 millisecond I/O weight for read, and even the even I/O weight for log writer, redo log writer is even higher. It's almost 11.5 millisecond. As a result of this huge weight, your CPU basically is not doing anything. So this shows your average SQL statement. You only spend less than 4% on CPU. You spend most of the time waiting for this I/O. So in this case, your I/O actually block everything. Your CPU is starvation. It's not doing anything. So that's why we need have some way to actually cut down this I/O weight. Later, I'm going to show you how this can be cut down. So let's come back to look at what exactly means PMem, block addressable. We mentioned that. So you could do, when you configure PMem, you actually possible you can force them to configure as a raw device or sector device. It is possible. But if you do that way, you will have this huge problem that potential risk to lose data. Because when you do block device, the application think you actually read by block, but in case if your system is down, the application think you can recover 4 block, but actually PMem itself only can recover 1 byte. So in this case, if you use PMem only can recover 8 bytes, but the application think you can actually recover the entire block, in this case, 512 byte. So you end up losing 512 minus 8. So that's 504 byte. You lose 504 byte data. So if you run the Oracle database, in this case, you end up your data file cannot be recovered. So you have a huge risk when you shut down database. If you store database on this raw device and you shut down database, there's a huge risk that when you bring up database again, when you power back, you try to bring the database again, your data file is corrupt. You cannot recover your database. So that's why it's not advisable to store the database, your Oracle database, in the PMem, which is configured as raw device or sector device. So do not configure your PMem device as a block device to store database. So never do that. So you have to use the bi-addressable. But the story was before 19C12, Oracle cannot handle. So bi-addressable is not supported on Oracle database before 19C12 release. So there has been about 2 years. If you look at the Oracle support link, there was actually a support link article mentioned that do not use the PMem app direct mode store Oracle database. That was not supported. So that's why when our team studied PMem, when we wrote that paper, we actually specifically hold down the PMem study, PMem app direct mode study. We only do the PMem for in-memory database, but hold down the study for PMem as an app direct mode for Oracle database. So we didn't do that until we wait Oracle provided support. So Oracle released the support, the 2 support for PMem app direct mode. One is 19C, one is 21C. So they approximately they release almost at the same time, but these 2 are a little bit different. But later we can discuss difference. But you'll probably also realize that Oracle Exadata AM or 9AM, they also use a PMem, but that's a different story. So in this case, in Oracle Exadata system, the PMem is used as a storage device in the storage server, so the way is totally different from the regular 21C, 19C database. In this case, we use PMem as a storage in the database server instead of a storage server. But you can list so far right now until today, until last year, you actually have a 3-way. Oracle has provided 3-way to leverage PMem app direct mode. The first way method is actually Oracle Exadata, which is only available for on Exadata. But for rest of non-Exadata database, you have this 21C PMem database file store. or Oracle memory speed file system in 19C, but you have to upgrade your database to 19C release 12, so patch set 12. So, and you also have to realize that these two, the only support single node database. The only Oracle rack support using PMem is available on Exadata. The non-Exadata machine support is only for single node database. So when Oracle released this tool, our team actually worked with the Oracle development team to actually validate it, also did a performance study. So the rest of the presentation basically will show you how we did it on this two study. So the first one is 21C. The Oracle actually released this almost same time at 19C. But in this 21C, Oracle guarantee two things. One is it's safe to store Oracle database in persistent memory as a file system. There will be no issue with data corruption. So that's the first thing. Without this, we simply cannot do it. So the second thing is Oracle 21C actually provided DEX support, which means the Oracle Oracle database query can directly read the data from PMem without copying the block from PMem to database buffer. So this is only for read, not for write. And this feature is only available for 21C, not in 19C. We'll talk about 19C. Yes. So this basically show you how we actually do it. So I don't want to. It's a lot of detail. We're actually going to write a paper about that. So basically, when you configure this PMem, you actually first you do you on the system level you configure this PMem. Then in OS level you create this namespace. In this case, namespace is very similar to device, but in this case, it's not block device. It is just device, PMem device. Then on top of PMem device, you create a DEX file system. So this is a command to create a SFX DEX file system. By using DEX file system, you can bypass the memory copy. Then on top of a DEX file system, you create this PMem file store. That is PMem file store mount point is actually where you the mount point of the file system that you actually can store data file. So remember this U1DB DB1 _ PMem. That is a mount point. And under this mount point, we can put all the data file. So look, see, all the data file is under this mount point. So this is the mount point. So you can put data file, online read log file, temp file, control file. So pretty much all the file can be put into the PMem file system. Then the rest of it is very same. But remember that people may have question, what happened to ASM? So in this case, if you want to use the PMem, you completely bypass ASM. You're not going to use ASM at all. This is only on file system. And you build a regular OS file system, in this case called or file store, on top of PMem, without worry about the ASM. That's one of the reasons that we cannot use the rack, because if you use the rack, ASM has to play a part of the role. But in this case, the PMem itself, since PMem itself is on server only, or one solely only, can but not be shared by other node, and also this is on a local file system. So this probably these two reasons together, pretty much is a great obstacle for us to actually implement a rack solution. So simply, if you do this, if this file system, local file system, you cannot do rack. And very similar to the 19C. So the only difference is you still can create an FX file system. On top of that, you actually create a file called UBER file. And then this UBR file is per database only. So if you have if you create this X file system, but if your server has multiple database, then you have to create a multiple UBR file. So remember, the UBR file name is actually have this Oracle SIN name to distinguish the file name. So let's say if you have 5 database, you're going to create a 5 UBR file, and the UBR file just give you the actually the simply like one point for each database. So then you create a UBR file. In this case, UBR file is for test database. Then mount this UBR file to some logical mount point. Then you can put all the file underneath this. Let's see what's the difference between the 19C implementation, 12C implementation, 21C implementation. So according to Oracle actually implemented 21C first, which Oracle considers this a complete solution for PMem. But they also want to make sure that 19C can take advantage of some of this feature. But I believe that maybe this is a time crunch or something. It is difficult because 21C PMem is completely new development. It's going to be, it's kind of hard for them to actually, in a short time, to bring back all the 19C. So that's why they took a partial of this the implementation and then put it back into 19C so that 19C can use that. So as we mentioned, the 21C Oracle support 2 things. One is no corruption. Second is DEX file system called direct mapping. So this feature is called direct mapping. So you actually establish a direct mapping from your buffer cache to DRAM, buffer cache to PMem, so that when you read the data, you actually don't have to copy data from persistent memory to DRAM. So this feature is called direct mapping. So 21C implement both. So it's safe to save data in the PMem file system. Also, they also implement direct mapping. But in 19C, they only implemented the first one, which is safe to store data file in the persistent memory. In this case, they call it memory speed file system. It is safe to store. By being able to store data in the PMem, you actually can directly leverage the speed because it is given that you can take advantage of the high speed I/O if you use the PMem to store data. So as long as you can guarantee data no corruption, you can immediately leverage the performance of the PMem. But the second piece is direct decimal support. So that is not available for 19C. So if you want to use both, you have to go to 21C. But if you want to use, if you just want to make sure that you can leverage the performance and you are safe to store data, and also your database is not able to move to 21C quickly, because according to Oracle, 21C is not actually production ready. It's not advised to you to move your production database in 21C, because the 21C has a very light, short lifespan. I think the support for 21C expires next year. So in this case, if you want to leverage the PMem advantage of PMem for high performance, you can take this route. So you actually upgrade your database to 19C R12. So just apply this R12 patch. I assume right now most people probably already upgrade to R12, because R12 was released like early of last year. So most people probably already in R12. So if you are in R12, you actually can do this. You can actually follow this step to, if you add a couple PMem on your server, you can just follow this step, configure this PMem, and make this Oracle memory speed file system, and then you will actually move data to all. So one thing I also want to mention is that both this feature are not support for DBCA. So if you want to create a brand new database use DBCA, right now DBCA cannot recognize these two file systems. So the Oracle recommended way is you create database on regular storage first, then use RMAN to migrate your data, all data file into this PMem file system, either 21C or 19C. So I just want to quickly show our performance study. So we did exactly 2 POC. One is for 21C, one is 19C, and at that time we actually use 6 PMem. Total we use 12 PMem, 6 PMem for 19C and 6 PMem for 21C. So all this performance is based on 6 PMem. So we remember we previously showed that the workload that we actually had we had this huge workload. So about almost 5 millisecond workload. The wait time, 11.5 millisecond wait time. So when we run the same workload, in this case using the 21C, I think this is actually this is 19C. Yeah, we use the 19C feature. So we were able to cut the sequential read wait time from almost 5 milliseconds to 30 microseconds. So that's from 5 milliseconds is about 5,000 microseconds. So we were able to cover from I think it's a 4,850 microsecond to 30 microsecond. That is more than 100 times, 150 times a reduction of the latency. Similar, we are able to cut from 11 millisecond to 81 microsecond. That is let's see, 10,000, almost 11,000 millisecond to 81 millisecond. That is more than 100 times. So this proves that by store the Oracle database file into PMem, we can significantly cut the I/O latency. As a result of this cutting, you can see that all the database CPU was fully utilized. So previously it was 3%. Now it is 97%. So which means by cutting the I/O latency, we're able to achieve a much higher throughput. So the previous throughput I didn't show. The previous throughput was like 500,000. So we were able to increase the throughput from 500,000 to 3 million TPM. So this is about 6 times increase of throughput, and the response time was more than 100 times reduction. And we continue the study by put a different workload. You can see that the TPM, when we add more workload, TPM increase. And nice thing about this, even we add a lot of more workload, the file latency, I/O latency, was not significantly increase. So from 20 to 50 milliseconds, all is much lower than the regular storage I/O. The one we tested before as a comparison, that was on SSD. So and this was on the PMem, and the CPU utilization is much higher. So. And furthermore, we actually did a 21C. We want to see, because as we mentioned, 19C only implemented one thing, which is, which is allow us to store the data file on PMem, but they didn't bring the direct map buffer cache mapping. So every time when you read the data, you still have to copy the data from PMem into buffer cache. But when we do the 21C, so they actually can skip a partially skip the copy. So I talked to Oracle about how this direct mapping works. So Oracle said that it makes sense too. Like, so if you read the data, what happens if you have a single statement that you need to read the data from PMem? So if you read the data, if you read the data that just for read, you're not going to have to change it. Then they're not going to copy data to a buffer cache. But if you have to read the data for update, you know, a lot of time you actually have a single statement that you bring the data in, then you have to update. In that case, the Oracle still have to copy data to buffer cache. Then you update it. Then of course the write back use database writer. So I guess the from here you can see that if you compare this, so the previous 19C, the database sequential read wait time was 30 microseconds. So this one is 23, so a little bit lower. I guess it's probably like in this case about 20% lower. Lower. So I was actually talking to Oracle about this. My personal impression was depend how your application. So if your application is more read only, less write, then this probably will further reduce, because all the data for those applications more like maybe like a 80% read application. So most of your read is for read only. You don't have to update. In this case, the Oracle automatically skip those copy, so they can actually directly read a file without a copy there. And but if you increase the write, if you increase the write percentage for 20 to maybe 40 or 50%, then Oracle has to do more copies. If you do more copy, the copy definitely take time. Even your PMem is very fast, but it still take time to copy data. You have to copy the data from PMem and to buffer cache. When you try to put the data in buffer cache, you still have to wait for the slot on buffer cache. Like you have to get a free list. There could be some free list wait there. So that's why this number could vary. But overall, but we still see the very similar high performance, even better performance, because we have a less weight for compared to 19C. And this number could be much lower if you have more read type of workload. And similar or even better performance than 19C. So both case, you can see that both case are very similar. You know, if you add more workload, the pattern is very similar to 19C. So I would think for sure, just by storing data into PMem, you will get a lot of huge benefit on the I/O. So basically, you will cut your I/O response time 100 times. That's based on a study. So, but the second option is direct mapping. From my own study, is based on the workload related, depending on what's the percentage you'll read and write, and that's what I found. So I know Oracle tried to advocate direct mapping because this is one of the huge benefit for using PMem. But based on my study, that is actually has a workload dependency on that. So specifically the workload I'm using is more like this kind of TPCC type of workload, which has about 60%, about 40%, at least 40%, or maybe 40% of the write. So that's why it's a little bit, you know, the delta is not that high between 19C and 21C, which means the direct mapping does not give huge jump as we did for compared to the comparison between compared to the benefit of just using PMem, PMem high-speed I/O itself. So that's what I found, and yeah. So that's all the thing I want to cover. So yeah, any questions